Hello and welcome to Teacher Talks number 2, Exploring the Fourth Dimension, Building a Tesseract. In this episode, we're going to look at one of the simplest shapes in the fourth dimension, the Tesseract, or the four-dimensional cube. And we're going to use a lot of the ideas that we use in our classrooms in order to explore this. We're going to use some analogy, we're going to use some patterning, we're going to use some justification, we're going to do some generalization, all this to try to understand this new object in terms of things that we already understand and see if we can figure out some of its features. So, hope you enjoy the ride. Okay, we're going to start our investigation by looking at a book called Flatland that was written by Edwin Abbott in 1884. The book is sort of a criticism of the class system that existed in Victorian England at the time, but who cares about that? We're interested in the mathematics. The main character is a square that lives in a two-dimensional space. And one day the square is visited by a sphere from three-dimensional space. Now, the square can't envision three-dimensional space, so the sphere then goes through a long period of time trying to explain what his space is like. And eventually comes up with a nice analogy for the square to be able to envision what a cube or a three-dimensional version of him would be. And later on in the book, a square actually takes that analogy one step further to envision what a four-dimensional cube would look like, even though the sphere rejects that there would be a fourth dimension. So let's take a look at the argument that they presented. So we're going to construct a cube and a tesseract, and the sphere says, okay, we're going to have these squares in various dimensions. If I go to the lowest possible dimension, dimension 0, which is only a point, my square is just going to be that point. Now, if I add a dimension and I want to make the square of a larger dimension, what I would do is I would take and make a copy of our point and join those things up with a line segment. And so that gives us a segment which is a one-dimensional cube or square. Similarly, to go into dimension 2, if I start with dimension 1, I make a copy of my one-dimensional cube in the new direction and join up corresponding points, I get a square. And we can go one step further, starting with a square. If I make a second copy in the third dimension, join up corresponding points, we get a cube. Now, we're already having a little bit of a difficulty because we're actually representing a three-dimensional object on a two-dimensional screen. Fortunately, this is an image that all of us should be familiar with. But when we go and take a square's extension, we're going to go into the fourth dimension. And he says, well, why can't we continue this process? If I start with dimension 3, I introduce a new dimension that's perpendicular to that. I make a new copy in this new direction, join up all the points, I get a four-dimensional cube. Now, because it's hard to draw a three-dimensional object in two dimensions, it becomes even harder as the number of dimensions go up. So this becomes a little bit messy, but there's enough there that we can kind of see some of the properties of this four-dimensional cube or tesseract. Later on, we'll come up with a better picture of a tesseract. But for now, we'll deal with this one. And we're going to see if we can find out some of the features. Now, important to notice, there's no reason that we have to stop at the fourth dimension. This analogy can continue to create a 5-dimensional or 6-dimensional, 7-dimensional, or whatever, however many dimensional cube you want. And I would encourage you to sort of explore this idea and see what you can figure out about these higher dimensional things that we can't picture, but through analogy, we can actually figure out some of the stuff that's going on. Okay, so let's find some patterns in the objects that we understand and can draw, and see if we can extend that to find out about what's happening in higher dimensions. So we'll start with the easiest thing to deal with, the points or the vertices of our shapes. So in dimension 0, we have a point, and so we only have one vertex. For dimension 1, it's a line segment, and it's going to have 2 vertices. In 2 dimensions, a square has 4 vertices. In 3 dimensions, a cube has 8 vertices. And hopefully you should see a pattern here that you'd be able to extend to the 4th dimension. But even if we go back to that crummy picture, we can see the vertices in that picture and count that there's going to be 16. And we see that if Vn is the number of vertices on an n-dimensional cube, which from now on I'll just call an n cube, then V0 is 1, Vn is just twice the number from before. And again, this makes sense just by how we construct it. At each new dimension, we're taking 2 copies of the dimension before and joining corresponding points. And that just gives us 2 to the n. Okay? So we would expect this pattern to continue, so that if I had a 10-dimensional cube, I'd expect there to be 2 to the 10 or 1,024 vertices on that. Okay, so let's look at the edges. This is a little bit more difficult. Again, we're doing that doubling each time, so we're kind of expecting a doubling to go on. But if we look at the number of edges, there's none for a point, there's 1 for a segment. When we go up to a square, well, we haven't just doubled the ones that we had before. We get some extras in there. And when we go from a square to a cube, we don't just double. Again, we get some extras. When we go from a cube to a tesseract, joining, counting those things out, again, we're going to have more than just doubling. So again, En is going to be the number of edges. We're seeing we're not just getting doubling going on here. So we're not going to have the same pattern that we did for vertices. But let's see if we can figure out what's going on by going back to the construction and focusing in on the edges. So 0 dimensions, we had a point. There's no edges on that. For 1 dimension, we're going to double what we had for 0 dimensions. So we're going to double the number of edges we had before, but we didn't have any edges before. But we get an extra edge when we join together those corresponding vertices from the doubling from the dimension below. So E1 turns out to be 2 of E0, which is nothing, plus 1, which corresponded to the 1 point that we had before, gets connected to its corresponding point in the doubling. If I go on to 2 dimensions, again, if I double what I had before, I don't have all of the edges, but if I connect the points from the original edge to their corresponding points, I get 2 more extra edges, which gives us our 4. Same thing in 3 dimensions, doubling gives us those ones. If I add in the number of vertices that I had for a square, I get my missing edges. So I seem to have found the pattern. Let's go one step further, and rather than draw this, let's see if it corresponds to what we had found from our counting. If I do 2 times the number of edges in 3 dimensions, and I add the number of vertices in 3 dimensions, I get 32, which is indeed the number that we had counted from our picture. So let's see how we can write down. So the number of edges I can write as E0 is 0. En is going to be 2 times En minus 1, so twice the number of edges we had before, plus the extra that we get when we connect the vertices. And there's actually a closed form equation for that. En is just going to be n times 2 to the n minus 1, which we can write as n choose 1 times 2 to the n minus 1. And I got this from the online encyclopedia of integer sequences. It's sequence number A001787. If you haven't explored the online encyclopedia of integer sequences, I would suggest that you do that. It's a lot of fun. Similarly, if we go on, I could say for faces, which are squares, I'm going to have 0 faces if my dimension is less than 2. So if I've got a point, well, there's no squares on a point. If I got a segment, there's no squares there. I have to get to dimension 2 before I actually get something. And I'm going to get the same sort of pattern. To get the number of faces, I'm going to double the faces that I had before because of our construction process. But now each edge is going to give us a new face. And if I back up a little bit to the cube over here, we can see that happening. If I go from 2 dimensions to 3 dimensions, I started with 1 square, I doubled to get another square, and now each edge, when I join the endpoints of that edge to the other corresponding new square, I get another face. So I get another face here where there was an edge, another face here where there was an edge, there and there. So that's why I get my 2 times 1 plus 4 gives us our 6. And again, we get a closed form formula for that thing. And now, again, we should start seeing a pattern. The number of one-dimensional things is going to be n choose 1, 2 to the n minus 1. The number of two-dimensional pieces is going to be n choose 2, 2 to the n minus 2. If you want, you can check out the online encyclopedia of integer sequences at its website here. So let's generalize this and see if this pattern actually continues. If I call d capital N sub n the number of d-dimensional elements of an n cube, first of all, what the heck do I mean by that? So 0 big N sub n is going to be the number of 0-dimensional elements of an n cube. So in other words, 0 dimensions are going to be points. So this is the number of points on an n-dimensional cube, which we call just Vn, number of vertices. 1n1 is going to be the number of one-dimensional elements of an n-dimensional cube. Well, one-dimensional elements are line segments. That's going to be our number of edges. And similarly, 2n2 is going to be the number of faces. But now we can continue this pattern. 3 and n is going to be the number of cubes in a n-dimensional cube, like a number of 3-dimensional cubes, and so on down the line. So I'm going to claim that the pattern that we saw before actually continues. And that is, this should make sense. D and K is going to be 0. The number of d-dimensional elements is going to be 0 if my dimension that I'm of the cube that I have is actually smaller than the dimension of the elements. Okay? And I'm going to claim that this pattern continues. I'm going to double to construct our object. So I'm going to take the object of one dimension lower, double. So that'll give me twice as many things as I had before. But again, when I join up the things that have one dimension less together in the new thing, those will also create one of these new things. And the closed form is going to be n choose d, 2 to the n minus d. In the next part, we're going to try to justify that these things actually hold. Okay, in this section, we're going to take a look at introducing a coordinate system to this. So with this different representation, we're going to see if we can look at those patterns that we developed in the last section and see if we can verify them by sort of introducing an algebraic notation. So first thing we should do is, again, deal with the cases that we are familiar with. So dimension 1, the graph is just going to be on a number line. The vertices are going to be the coordinates 0 and 1. In dimension 2, I've got a square. It's going to have coordinates, and again, I'm dealing with a unit cube here so that I'm making side lengths 1 so that I've got sort of a standardized set of coordinates. So I'm going to have the coordinates 0, 0, 1, 0, 1, 1, and 0, 1. And similarly, in 3 dimensions, I can list the 8 coordinates that I have. Now, from there, I see that these vertices are just going to be an ordered n tuple. So if I'm in 7 dimensions, I'm going to have an ordered 7 tuple. If I'm in 23 dimensions, I'm going to have an ordered 23 tuple. But the coordinates are going to be just zeros and ones. And I'm going to have every possible collection of those things. Looking back at the ones that I had the complete set, which means that the number of vertices is just going to be 2 choices for the first coordinate, 2 for the second, 2 for the third, and so on. So I'm just going to have 2 to the n possible ways that I can fill up my ordered n tuple with zeros and ones. And that agrees with what we found in the first section. So that's good. So let's see if we can do the same thing for the edges. So for edges, we're going to think of it in terms of the endpoints. So in 1 dimension, my only edge is the collection of those 2 points. In 2 dimensions, I've got 4 edges, which are collections of 2 points. So 0, 0, 0, 1 is an edge that joins those 2 points. And similarly for the others. And similarly in 3 dimensions, I've got those 12 edges. Now, let's take a look at these things in a little bit more detail. Notice that in each collection of 2 points, in 2 dimensions, one of the coordinates is fixed, and the other coordinate goes through what we defined as an edge in 1 dimension. An edge is 1-dimensional, a line segment, and it was something that joined 0 to 1. Well, if I fix this coordinate as 0, notice my other coordinate goes 0, 1. If I fix this coordinate at 1, it goes 0, 1, and same thing for the others. If I go to 2 dimensions, now I'm fixing 2 of the coordinates, and the other one's going through 0, 1, 0, 1, 0, 1. So let's try to count with that in mind. So the number of edges is going to be, first of all, I have to pick the coordinate that is going to go through the 0, 1. Well, how many ways can I do that? Well, if I'm in n dimensions, there's n coordinates, so there's n choices for picking the coordinate that's going to be 0, 1. Now, what about the other coordinates? Well, notice that if I pick this last coordinate, I've got 1, 2, where's the other ones? 3, 4, edges that have the last coordinate going through. And if I look at the purple numbers, I get 0, 0, 0, 1, 1, 0, 1, 1. They go through every possibility. So how many possibilities? Well, I've already used up one coordinate, so I've got n minus 1 coordinates left. Each of those coordinates can take on 2 values, so I'm going to get n times 2 to the n minus 1, which n is the same as n choose 1, which, again, I'm really picking one of the n coordinates to use as my edge that's going to go 0, 1. And that agrees with what we found earlier. So that gives us a little bit of confidence that possibly what we're doing is correct. But let's look at it another way. So if I look at the edges and I pick a particular coordinate, so in 2 dimensions, if I pick the coordinate 0, 1, notice it's part of 2 edges. Why is it part of 2 edges? Well, if I look at the other coordinate, it's going to differ in 1 position from this. So here, if I change the 1 to a 0, I get that coordinate. If I change this 0 to a 1, I get that coordinate. So it's going to be joined to every coordinate that differs by 1. Well, there's 2 coordinates, so there's 2 places that I can do it. Similarly, in 3 dimensions, I'm going to have each vertex is showing up on 3 edges. Why? Because it's going to be joined to another vertex whose coordinates differ in only 1 position. So let's count using that idea. So the number of edges is going to be the number of vertices, and for each vertex, it's going to be connected to the same number of points as there are dimensions. So n. Now, we got to be careful, because if I look at this, 1, 0, 1 is connected to 1, 0, 0, but notice 1, 0, 0 is there, 1, 0, 0 is there, 1, 0, 0 is there. So this point is also part of the 3-point collection for 1, 0, 0. So if I do this, I'm actually counting each edge twice. I'm counting it once for each endpoint. So to correct that, I have to divide by 2. And if I put that together and simplify, I know that Vn is 2 to the n. If I work that out, I get n times 2 to the n minus 1, or n choose 1 times 2 to the n minus 1. And again, we verified this thing. Looking at it from that different point of view, I get the same formula. That gives us a little bit more confidence that what we've got here is actually the formula for the number of edges. Okay, so let's go one step further and we'll look at squares on a cube and on a hypercube to see if we can get that formula verified. So here's all of the faces of a cube, and again, a square is just going to be a collection of 4 points, which are the 4 corners of it. So there's our 6 faces. If we look at each of those collections, for each coordinate in each of these collections, one of the coordinates is fixed. So in this one, the first coordinate is fixed at 0, here it's fixed at 1, here in the middle is 0, here in the middle is 1, and so on. What happens to the other 2 coordinates? Well, the other 2 coordinates now go through the 2-dimensional coordinates for a square. 0, 0, 0, 1, 1, 1, 1, 0. 0, 0, 0, 1, 1, 1, 1, 0. 0, 0, 0, 1, 1, 1, 1, 0. And the same thing down the line. So, if I look at the number of faces in 3 dimensions, first thing I've got to do is pick the 2 coordinates that I'm going to use for the squares. So there's 3 choose 2 ways of doing that. I've got 3 coordinates. I'm going to pick 2 that are going to occupy the coordinates of the square. Now my other coordinate has 2 possibilities for it. So there's 3 minus 2. I've used up 2 of the coordinates. I've got 1 left, and there's 2 possibilities, 0, 1 for that. And so that gives us our choice. So we see here's our 2 choices where I pick the last 2 coordinates. Here's our 2 choices where I pick the first and the last. And here's our 2 choices where I pick the first 2. And so for Dimension 3, it seems that our formula for the faces works. Let's go to dimension 4. Now, when we get to dimension 4, it's going to get a little bit messy because I was representing a square by the collection of its vertices. Well, I'm going to have 4 vertices on a square, so that's 4 ordered 4 tuples that are going to represent each square, and I've got 24 of them. So that's going to look a little bit messy on the screen. So I came up with a sort of a shortcut of representing that. So if I had a particular face, which is made up of 4 points, and again, 2 of these points are going to be fixed. So the first and the third are fixed at 1, 0, 1, 0, 1, 0. The other 2 coordinates go through the coordinates for a square, 0, 0, 0, 1, 1, 1, 1, 0. I'm going to represent that in a compact notation. I'm going to write 1, 0 in the first and 3 coordinates to show that those 2 coordinates are fixed. And I'm going to use S1 and S2 to show that the coordinates of the square are going to occupy those 2 positions, but that really represents the 4 different possibilities. So using this sort of compact notation, here's our 24 different squares on a tesseract. And if we look at that, again, we're going to have, I can have my square coordinates in the last position, I can have it in the second and fourth, I can have it in the first and the third, and so on. So if I want to count the number of faces, I could say, well, out of the 4 coordinates, I want to pick 2 of them to correspond to where the square is going to go. And if I look at my rows correspond to each of those choices, either the last 2 positions, second and fourth, first and fourth, second and third, first and third, or first and second. And for each of those choices, now for the remaining 4 minus 2 or 2 coordinates, they can go through all their possibilities. So I've got 2 other coordinates. They can go through all their possibilities. They can go through 0, 0, 0, 1, 1, 1, 1, 0. And same thing here, 0, 0, 0, 1, 1, 1, 1, 0. So the 4 columns correspond to the 4 different possibilities for our other 2 coordinates. And so that thing matches as well. And you can kind of go through the same sort of argument for any dimension and any size of piece that you want. If I wanted to have the number of 4-dimensional pieces of a 7-dimensional cube, I can imagine my ordered 7 tuple. The 7 choose 4 is going to be the number of ways that I can pick the 4 coordinates that I'm going to embed my 4-dimensional cube in. And the 2 to the 7 minus 4, or 2 to the 3, is going to be how many ways can I fill up the other coordinates. In this final section, we're going to use, again, analogy for what's happening in 3 dimensions to help us to understand what's going on in 4 dimensions. And this time we're going to try to understand sort of spatially what's happening. In the previous sections, we developed some patterns. We saw some relationships for the various elements of n-dimensional cubes. So that we could predict for any dimension, what its makeup is going to be. But here for the 4-dimensional cube, we're going to try to get a sense of how it actually is put together and what its structure is. And again, we're going to use analogy for 3 dimensions. And we're going to develop sort of a different picture of a cube. And so we've got here another picture of a cube that, again, should be known to most of you. In this case, we can think of this and interpret this picture 2 ways. One way we can think of it is we're looking into a box where the green is the bottom, these guys are the sides, and the purple around the outside is the top. The other way we can think of it is if we had a wireframe cube and we were taking actually its shadow projected onto a screen. So if the light was above it and going down, this is sort of what it would look like. And if we look at understanding where the faces are, again, the big square on the outside is that one face. If we're thinking of this as looking into a box, it's sort of the top of the box. The little one at the back is the bottom of the box. The trapezoids above and below would be, if I'm looking in, sort of the top and bottom of these things, and 5 and 6 would be sort of our left and right squares. Now, another way that we can represent a cube is with its net, and with its net is basically what we get if we undo some of the edges and flatten this shape out from 3 dimensions to 2 dimensions. So let's focus in on face number 2 here, and we see that it's attached above and below by 3 and 4, so those are going to be squares that when we slice here and slice here, slice here and slice here, I can fold 3 and 4 down. Similarly, 5 and 6 can fold down onto the left and the right. And all that's missing is that outside one. Now, if we look at our net that we have so far, we can see that sort of the space between 3 and 6 here was actually where that edge was. So in other words, these things would connect up. If we're going to make the cube, these guys connect up, these guys connect up, these guys connect up. So if I look, the only edges that haven't been used are these ones on the outside, the 4, that would correspond to the 4 edges that it would share with the top of this thing, which means that basically I can put the 4th square on the end of either of these things. Sort of for a nice symmetric net, I'm going to use this notation, and this is kind of a standard one. And this will help us to understand the 4-dimensional one, because we're going to do the same construction in 4D. So here is what I find a more useful visual representation of the tesseract, or the hypercube, or the cube, the 4 cube, where now instead of having our extra dimension just being a different direction in 2D like we did with the edges, we can think of the extra direction as actually being a growing direction. So I've got a smaller cube inside a bigger cube with corresponding edges attached. And the nice thing with this corresponds to either looking into a 4-dimensional box or the shadow of a 4-dimensional box, where now the shadow of a 4-dimensional box is actually a 3-dimensional object. So we could project a hypercube into 3-dimensional space, and its shadow would be 3D. And this is something that we can actually construct in 3D and get a sense of it. So just like for our 2-dimensional picture of the cube, we had a little square on the back. This becomes our little cube that's the bottom of our hypercube. The big cube is the top. And attached, if we can kind of picture what's going on here, I'm going to get these, looks like truncated pyramids, square-based pyramids, that have one face on the bigger one face on the smaller one, and these 4 trapezoidal sides connecting them up. And so on each face of the smaller cube, going to each face on the larger cube, we have some of these things. So let's unfold this into the net. So we'll do the same sort of thing that we did with 2 dimensions. We'll start with the guy in the center. And just like with the 2-dimensional case, we saw that the guy in the center was attached on each of its faces to another square, or each of its edges to another square. Here, on each of the faces of this inside cube is going to be attached another cube, because these truncated pyramids that we see are actually cubes, but because of the representation that we're using, they're being distorted in exactly the same way as the squares were distorted to look like trapezoids in our representation of a cube. So on the sides of each of the faces of the cube, I'm going to build another cube. So there's one cube with 6 more cubes attached to it. And again, this is harder to picture. It'd be better if we actually use something like linking cubes. And you could see how the things that are beside each other, the corresponding faces would actually be attached. So we can get a sense of how this thing would fold together to attach. And we'd have all of the faces going to the ones that are beside it, with the exception of, for each of those extra cubes, there'd be one face left over on the outside, sort of pointing outward, which would be the one that attaches to the purple. And again, the purple one could attach to any of these on the outside, but again, for symmetry and to sort of match our analogy for the other one, we're going to attach it here so that it looks like, if we did it out of linking cubes, like the cross that we had before, but with sort of an extra cube sticking forward and sticking backwards. And we can actually see that relationship that we saw before, that if I'm going from a 3-dimensional cube to a 4-dimensional cube, and I want to see how many cubical pieces there are, I duplicate the cube. So there's my 2 times my 1 cube. Plus, for each face, I get another cube. So I'm getting 2 times cube of dimension 3 plus face of dimension 3 to get our 8 cubical faces of the tesseract. And again, we can kind of see how this thing is going to fold together by analogy, by looking at what happened with the 3-dimensional case. This is actually depicted in modern art. Salvador Dalí created this painting, which he named Corpus Hypercubus, of the Crucifixion of Christ, on a 4-dimensional, the net of a 4-dimensional cube, which resembles a cross, but he was sort of using the fact that we can't picture what a 4-dimensional cube actually looks like to give some connection to the divine. So that's sort of an interesting place that this thing is actually showing up. So that's the end of that. I hope you enjoyed this episode of Teacher Talks. Next year, I hope to continue this idea. We might try to do some in person that maybe we'll film and post online so that everybody has access to it. But we'll see how things go next year. Until then, have a great summer, and we'll see you in the fall.